That way people can refer back to this video later. All right. So can someone online confirm that you can see the PowerPoint and then you can hear me?
I can see the PowerPoint and I can hear you.
All right, good to go. So again, it's a little early, but I guess I'll just use this time for announcements and reminders. Obviously, like I said in that announcement that I made on Google Classroom yesterday, I'm still pretty far behind between this class and the other class. So I still have a lot of grading to do if you're wondering why you haven't received your grades yet for the lab or the independent work you've turned in. So when I am done, I'll make a class announcement. And if that at that point you're like, hey, I didn't get this thing graded, then contact me and say, well, you said you're done grading, but I turned in this assignment and I didn't get a grade. So hopefully I'll get caught up today. What else to tell you? I'm thinking about not doing lab this week because in a normal circumstance, when we don't have this online option, we normally would not even have lab this week, because if we did, that would mean section 1 wouldn't have a lab because we didn't have class on Monday, right? And section 1 has lab on Monday. And that would mean section 2 would have a lab, and that would throw us all off. And even though technically it's an online lab, I guess it's not fair to you, because if you're section 1 and you've set aside that time every Monday, you know, to do lab work, but that was our day off, it's not fair. So we're not going to do a lab today, which means I'm going to have to make some adjustments to our tentative lab schedule. So yeah, for the week, don't worry about lab. I remind you to get your independent work done. What else to remind you? I guess that's it. If anybody has any other questions, let me know now or meet me on. Yeah, question?
I have a question.
What's that? I thought we had a question.
I have my independent work for last week, but I couldn't find out.
Shoot. Well, you're breaking up, but I heard you say something.
I still have it. I just don't know what it is.
You were breaking up, so I couldn't hear what you said. I knew it was something about independent work. So I guess if you can, just meet me during office hours, and then I can explain anything you need about independent work. Any other questions? All right, it's 8 o'clock. Let's jump into it. So a lot of people I know take biology because they don't want to take chemistry. So if that's the situation you're in, and I have to apologize to you because right now we're about to jump into some chemistry. For those of you who have had chemistry and thought it was a hard subject, good news is this is like the easy version of chemistry. We're not getting into the really hard stuff. We won't be balancing any equations or anything like that. You're just going to learn the basics. We'll go ahead and jump into it. Like I said, every chapter starts with this where they say, hey, why does this chapter matter? Usually we play the game, or usually I wouldn't. Usually I would skip it online, but this one's kind of somewhat decent, worth talking about. I'll just mention really quickly, your book talks about the top left. If you can't tell what that is, that's a dead coral reef. And the reason that's relevant to chemistry, your book points out that like a car exhaust in Boston, for example, like giving off pollution, even that far away in Boston, could end up killing, you know, coral in the Great Barrier Reef. Obviously, that's just some copper. You're going to learn about something called essential elements. That's what that is. And then I like this one. I'm sure you can tell what that is, right? That's salt being put on fries. And the reason I really like that one, and we'll talk about it later in this chapter, is you see a lot of people try to scare you with chemistry. One, because they'll use a chemical term instead of the actual, like, instead of saying salt, you might say sodium chloride, and that might be scary. Or they might say, here's some ingredients in this thing. Ooh, that's so scary. You don't want to eat that. And you could do that with salt. Because I could say, this is sodium chloride. Sodium is an explosive metal, right? And chloride is a poisonous gas. And both of those things are true. But so separately, they are deadly. Put them together, and it's regular old table salt, which too much of it's bad for you, but you actually do need some of it in your diet. And we'll talk about that in this chapter. So all these things, that's just an introduction, so I'm not going to take questions yet because we're going to come back to it. Nothing on this little part's ever going to be on the exam. I'm also going to go through this one pretty quickly. Again, every chapter starts with biology and society, and it kind of gives you this little scenario of something that's relevant to that chapter, and then hopefully would make you think to yourself, ooh, that's relevant to my everyday life. Long story short, for this one, they talk about radioactivity and how it could be bad for you, but how it's also good for you because we use it for medicine. We talk about the big differences between it being bad for you and being good for you. Is if it's bad for you, it's usually a lot of radiation that you get, and it's usually uncontrolled, sort of like this nuclear explosion in Hiroshima. And when it's good for you, it's usually in medicine. Like I said, it's very controlled. But anyway, none of that's going to be on the exam either. Anything that comes in its biology and society will not be on the exam unless I say otherwise. And I've actually seen something like this in action. My mom had a brain and sinus and skull cancer. So she had radiation actually kind of in the same spot of her head. So it's interesting. Anyway, skip through all that because, again, time is of the essence. So this chapter is broken down into two major concepts, some basic chemistry followed by water and life. So let's jump into some basic chemistry, and then that's probably where I'll start taking questions. So you might be asking yourself, well, why do we even need chemistry? This is a biology class. And the reason is because when you take down any biological system, eventually it all comes back down to chemistry. And if you're wondering what I mean by biological system, I'll remind you of that slide we looked at, I think, on Friday, where like at the very bottom, it was atoms and molecules, and then it was organelles, and then it was cells, and then it was tissues and organs, and then organ systems and organisms, right? So it goes from small to big. That's what we mean by systems. So even if you're looking at the whole entire biosphere, and then you get more specific to ecosystems, and then communities and populations, smaller you get, eventually you're going to end up at the chemical level. So that's why we have to learn about it. For your everyday life, it's because reactions are always occurring in the human body. So if you read up on the new vaccine and how that works, I mean, technically we're talking about mRNA and things like that we'll talk about later in the semester. But when you get down to it, all those things that you're going to learn even later are technically chemical reactions. So are there any questions so far? All right. Let's talk about the real basics. Hopefully a lot of this part, at least this next bullet point, hopefully will be a review for you. We're going to talk about matter and elements and compounds. Does anybody know what matter is? Or probably a lot of you do. You're just trying to think now that I'm sitting in a biology class, what is the proper answer, right? Matter is anything that occupies space. So you need to know that. Anything that occupies space and has mass. So basically matter is just stuff, right? Matter is stuff. There's 3 states of matter. I'm sure you guys already know this. Does anyone know the 3 states of matter? Yep, that's right. Solid, liquid, and gas. So everything on there so far you should know. Know what matter is. Know the 3 states. Though to be honest, I probably won't ask you the 3 states on the exam because that's just too easy almost. So then, what is mass? Does anybody have any idea what mass is? That's all right. You will now. It's the measure of the amount of material in an object. So in layman terms, matter is stuff, and mass is how much stuff, right? Before we talk about elements, does anybody have any questions about matter or mass yet? And the most important thing about matter and mass, as far as what's on the screen and having to know these definitions, it's mostly because you just need to know what I'm talking about when I use those words. It's less important, again, for the exam. But when I use these words, as I will in this chapter, you need to know what I'm talking about. Same with element. An element cannot be broken down into any other substance by a chemical reaction. So, gold is gold. If you try to break that down anymore, like if you have 1 atom of gold, if you try to break it down anymore, it's no longer an atom, right? You have to take off electrons or protons or neutrons or these other things, that I'm going to teach you about later. So you've broken it down as far as you can. And if you break it down any more, it will no longer be that particular element. And as your book points out, all matter is composed of elements. So any questions about anything on this page? For the record, I don't make these memes. I just find them without even looking for them. I run into them when I see them. I'm like, oh, I'm going to save that one for this PowerPoint. Your book points out that there's 92 naturally occurring elements. If you look at a periodic table, that's the big section, not the little small section on the bottom. That's nothing for you to know. I'm not going to ask you how many elements there are because, again, this isn't a chemistry class. I'm just trying to teach you the chemistry that you need to know to understand biology. So there's no need to know that there's 92 occurring elements. Why your book chose these 4 examples, I don't know, but some examples are carbon, oxygen, potassium, and gold. Carbons are really important. You're going to learn a lot about that. Oxygen, obviously, you need that to live. You breathe it. You're also going to learn a lot about oxygen later. Actually, sorry, can you guys make sure you're sitting in the spots with the green boxes? Some of you are. I forgot to mention that when you came in. I apologize. Yeah, so if you can sit over there, just in case. If my boss comes in and sees you guys sitting anywhere, I might get in trouble. Anyway, so yeah, those are some examples. Each symbol, like again, if you look at a periodic table, each symbol is derived from its English, Latin, or German name. Again, these are not things that you need to know for the exam. I don't care if you know them or not, because even if you forget what I just told you, you'll still be fine for the rest of this chapter and therefore the rest of the semester. So it was in the book, so I included it. Any questions about this slide? All right. Well, if you happen to be interested in this kind of stuff, that's an idea for independent work. You could write some short paper, come up with some element that you're interested in, and read up about it. Some of them are interesting, like how they were discovered or what they do, how rare they are, things like that. There's the periodic table. You can see up there, we're using carbon as an example, where it's got the atomic number and the element symbol and the atomic mass, and you're probably wondering, what is that? And I'm not going to talk about it right now because it's going to be in the next couple of slides. But yes, there's the periodic table. There's your 92 naturally occurring elements, and those are your artificial ones down there. Any questions on what the the periodic table is? And again, I'll explain the details of the symbol here in a second. All right, you guys are really easy today. Here's a quick guessing game. This will not be on the exam either, but I know chemistry can be really boring, so I tried to come up with something at least relatively interesting. Let's see if anyone can guess what element this is, either based on the picture of the element or this goofy picture. Oh, man. It's a young crowd then. Every semester, I get fewer and fewer people getting it because every semester, you guys get younger and younger. So the element is mercury. Sorry if you were about to guess it, but yeah, it's mercury. And it's supposed to look like Freddie Mercury. For those of you who don't know who that is, that was the lead singer of Queen. This one's another one. At least hopefully you can understand. You should guess it by the actual element as opposed to the picture of that person. Because again, this is an old person thing, I think. But any guesses what that element is?
Copper.
Yeah.
Copper.
Yep. And that's some old guy named David Copperfield. I don't like magicians. No offense if any of you are magicians. I've just never been interested in watching that. It always creeps me out for some reason. Anyway, here's another old person one. Man, they're all old. Any idea what this is?
Zinc.
Good guess because of that Z. No, it's lead. Even though it's spelled differently, those are the symbols for Led Zeppelin. All right, here's one for the younger people. Iron, yeah, right? It was Iron Man. Okay, anyway, we're done with goofing off. We'll get back to it. Obviously, none of that's going to be on the exam. I'm not going to give you a picture of Freddie Mercury and be like, what element is that? But here's some stuff you do need to know. And I'm not really big into numbers in this class, like at all. So when I give you a number and say you should know this, then you should know it. There are 25 elements that are essential to people. So of all those 92 naturally occurring elements, 25 of them are essential for us to live. 4 of them make up 96% or about 96% of our body weight. So far, here's the number you need to know. 25 essential elements. Now, yes, the other 4 make up about 96% of the body weight. That's a number you don't need to know. Just know what I call the big 4. So when I ask you on the exam, what are the big 4, and that's how I'll call them or something like that, just know that they are oxygen, carbon, hydrogen, and nitrogen. And again, you don't need to know that it makes up about 96%. You just need to know almost our entire bodies are made up of those big four: oxygen, carbon, hydrogen, nitrogen. The good news is by the time we're done with this chapter, and by the time we're done with the next chapter, and by the time we're done with the chemistry lab, you'll have those memorized. So that's one of those things you probably don't even need to study, because we're going to keep talking about those four elements so much. So any questions so far? All right, so again, those are the big four. That's what most of your body's made of. And that's really going to make sense later when we start talking about, because right now we're just talking about elements. When we start talking about all these important molecules in your body, you're going to notice this is nearly the only thing we talk about. There are some other ones, and we're about to talk about those. So again, about 96% is the big four we just talked about. So then you should be asking yourself, well, what about the other 4%? What are they made of? And they're made up of 7 elements. Your book lists them. I'm going to talk about them, but you don't necessarily need to know them. And I'll tell you what I mean when I'm done talking about them. But the first one is calcium. Calcium is important for bones. It's important for teeth. You can find it in dairy products, sardines, and green and leafy vegetables. This is not a nutrition class. This is not a human anatomy class. So as far as I'm concerned, you don't need to know that. I'm just talking about it because your book's talking about it. Phosphorus is an important one. It's a component of DNA and also something called ATP, which we'll talk about later. You can find it in eggs, beans, and nuts. Let's talk about, and the only reason I'm going through this quickly is, again, because I'm not going to require you to know any of this. But before we talk about the other 5, are there any questions about these 2? And again, your book included this, so did I. Yeah, sorry, maybe I don't have the slide. Yeah. So again, there's 7 of them. We've only talked about 2 because that's the one your book talked about. You do not need to know any of those. You just need to know the big 4, the ones we talked about earlier: carbon, oxygen, hydrogen, and nitrogen. So again, we're just talking about these. You don't necessarily need to know them. So those are the other 7 elements. And then there's these 14 elements that we call trace elements. And these are interesting because they are less than 0.01% of your weight. And that's not a number you need to know, but just letting you know there's a very small amount of them. And even though there's a very small amount of them, they are essential. Like, you wouldn't live without them. And this is also a good idea for independent work. As I move forward and tell you about some of these trace elements, keep this in mind. Again, you need some of them. You need a small amount of it because you'll die without it. But also, some of it, if you have too much of it, it could kill you. Anything's like that. When people say, oh, that's poisonous, technically anything could be a poison. It's all about the dose. But obviously these things, since they're trace elements and you require such a small amount, then it wouldn't take much before it would become poison. So anyway, back to the independent work idea. If you want to, look into some of these and say, okay, what happens if you don't have enough iodine? What happens if you have too much iodine? Things like that. So that's something to look into. Like, how much is too much? How much is not enough? What are the results of too much? What are the results of not enough? Anyway, let's start with iodine. I'm sure you guys are familiar with this, even if you're not familiar with this, because if you get a thing of salt and it says iodized salt, that's what that means. That means they've put iodine into the salt because you need it. If you have a deficiency of it, it causes these things called goiters. I don't know if you can see the woman on the bottom right. That's what a goiter is, right? She has her thyroid gland. It's very enlarged. She looks very unhappy about it. I don't blame her. I would also be unhappy. Where can you find iodine other than the iodized salt I told you about? You can find it in green vegetables, eggs, seafood, dairy products. Yeah, so that's iodine. Again, that's the book example, so I'm talking about it, but it will not be on the exam. I think it is on the study guide, but it won't be on the exam. So any questions about iodine before we move forward? All right, fluorine. I'm sure you're familiar with fluorine. It's added to dental products like certain mouthwashes and toothpaste, and it's also in drinking water, right? Sometimes municipalities will add fluoride to the drinking water because it helps maintain healthy bones and teeth. And unlike that last woman who looked very sad because she had the goiter, this guy's having some teeth issues, but at least he's happy, right? So that's fluoride. This is a big one. Again, for independent work ideas, if you're looking into how much is too much, this is a good one, because this is one of those conspiracy theorist things that people love to talk about. Like, they're adding poison to your water. Yes, it's a poison if it's too much, just like everything else is, but really it's needed. So it's one of those interesting things to look at. And also, some of it is too much. Like for children, right? You don't want too much of it for children as well. And that's why a lot of children toothpaste, like the first ones you give them, don't have fluoride in it because too much is too much. So anyway, just something to think about, something to look into. Any questions so far? All right. There's also some trace elements in food. Like I said, we talked about the iodized salt. This one is an interesting one. Iron. So when I say iron, they literally mean iron, like there's metal. So if something says it's fortified and has iron in it, that means they've literally put metal into the cereal, which might sound scary, but it's something you need. You need that for healthy blood. And if you click on the top left, like if you download this PowerPoint, click on the top left, there's a video you can watch. There might be two of them. This is great. In both videos, they do the same thing, but there are two different styles of videos. One of them is an educational video where you see this guy and he's like, I'm going to demonstrate to you that there's iron added to this cereal. So he takes some cereal like that and he blends it in with some water so it's a nice even mush. And then he gets a magnet and holds it up to the side of the blender and you can see the iron go there. It's like, oh, that's nice and educational. I told you that's how iron works. And the other one did the same thing, just trying to scare you. Like, do you realize they're putting metal shavings in your into your cereals? And she did the same thing. She blended it and put a magnet, and again, same results, but it was all about how it was presented. One guy was being educational because they're not hiding it. Like they even say, this is fortified cereal, right? They're proud of it. But other people, again, if they're not educated, they just love to scare you. But anyway, watch the video if you want. It's an interesting thing, I think. So any questions so far? All right. This is kind of a graphic, excuse me, of everything we've just said. So here again are the big four, and those are the big four you need to know. You need to know it's oxygen, carbon, hydrogen, nitrogen. You need to know those are the big four. You do not need to know the specific percentages. So I'm not going to say, you know, what percentage of your weight is oxygen, and you don't need to know it's 65. You don't even need to know the order of the big four. So you don't need to know that it's mostly oxygen, followed by carbon, followed by hydrogen, followed by nitrogen. No need to know any of that. Again, then there was the other seven, right? So we talked about the big four, we talked about the other seven, and then we talked about the trace elements. So again, if you were interested in what I was talking about for independent work, there's your list, right? You can look at any of those, figure out how much is too much, figure out how much is not enough, figure out what happens if you have too much, what happens if you have not enough. So any questions about this graphic? All right, nice and easy. So now we're done talking about elements. All right, so again, elements are the small things. Let's kind of kick it up a little bit. Let's talk about compounds. A compound is anything that contains two or more elements in a fixed ratio. And you don't necessarily need to know that definition for the exam. You just need to know what it is because it's a word I'm going to use. So you need to know what a compound is. When I use the word, I don't want you scratching your head being like, I have no idea what he's talking about. So yeah, two or more elements in a fixed ratio. And what do I mean by a fixed ratio? For example, water is always H2O. If it's anything different, if it's a different ratio, it is no longer technically considered water. So that's what we mean by a fixed ratio. And obviously, it would have to be two or more, because if it's just one, then that's just an atom, right? That's just an element itself. Your book gives some examples of compounds you're probably already familiar with. Water, I already mentioned. Sodium chloride, and again, this kind of goes back to what I was saying at the beginning of the class, where sodium by itself is explosive. When they store it in oil, because if it comes in contact with water, even water in the air, if there's enough humidity, it explodes. And chlorine, that's a toxic gas. You're a history major and in the military, so you're probably familiar with, you know, how they used that in World War I a lot, right? So it's literally something that was used to kill you. But you combine that with the explosive metal, and you get nice, delicious table salt. So again, those are just examples too. So I'm not going to say, you know, give me some examples of common compounds. Those are just examples. And are there any questions about those examples or what a compound is? All right, I'm going to try to slow it down, even though you guys aren't asking questions. I do know this is a lot of information, and I do know a lot of people aren't good with chemistry. So I'm going to slow it down a little bit. Let me see. Talk about this. Sorry, I'm just thinking about how far I want to go today. again, because I want to slow it down. All right. Anyway, let's jump into atoms. Well, you already know what an element is, right? If an element is anything where you can't break it down anymore chemically, otherwise you no longer have that element. So as a reminder, that's what an element is. Each element consists of one kind of atom. And you need to know what an atom is. Again, not necessarily that I'll ask you the definition, but it's a word I'm going to use a lot, so you need to understand what I'm saying when I use it. An atom is the smallest unit of matter that still retains the property of an element. So basically, it's the most basic unit when it comes to chemistry, right? When it comes to elements, an atom is the smallest thing you can have. Sort of like in life, you could say like the most basic unit of anything living is the cell, right? Yeah, technically you can break a cell down. There's different parts of a cell, but that cell is the most basic unit of life. Just like an atom is the most basic unit of an element. So you could still break that down just like you could break down a cell. You can see in this picture that there are different parts of that atom. And in the coming slides, we will talk about those different parts. But again, if you were to break that down anymore, you technically wouldn't have that element. You would have broken it down to something different. And like I said, we'll talk about that here coming up. Does anybody have any questions so far? All right, so now that we know what an atom is, let's talk about what atoms are made of. The structure of atoms. And again, I hope this is a review for a lot of you. So atoms, as far as we're concerned in this class, are made up of 3 parts. Technically, those 3 parts as a whole are called subatomic particles. I don't even care that you know that, but I do want you to know the 3 parts. Protons, electrons, and neutrons. You need to know those 3 parts. They also have charges, and you need to know that. And the good news is, there's an easy way to remember it. Obviously, neutron is neutral, right? That's the easiest one because it's in the name. Neutron, neutral. Proton, that's kind of in the name, right? Proton, positive. It's alliteration, right? That sounds similar. So electron's the hardest because it's not in the name, but by process of elimination, if you can remember that neutrons are neutral, and protons are positive, then obviously the only thing left is for electrons to be negative. Another way to remember it is if you get electrocuted, generally speaking, that's a negative experience, right? So think about that. That's an easy way to remember. So if you're looking at a particular atom, and if the protons, the number of protons in an atom, equal the number of protons, the electrons in the atom, like in this picture, this hydrogen has 1 proton and 1 electron. This gold atom has 79 protons and 79 electrons. So if that happens, then we consider the atom neutral because it has 0 charge, right? Because all the positives and negatives equal themselves out. And in this class, you can assume every atom we talk about is going to be neutral unless I say otherwise. So again, atoms are made up of 3 parts: protons, electrons, neutrons. Protons are positive, electrons are negative, neutrons are neutral. And if the protons equal the electrons, then they're equal. So that being said, what do you think would make something negative? What would make an atom have a negative charge? What would it need more of, or what would it need less of? What is it? Yeah, someone back there said more electrons, right? So if something has more electrons than protons, right, if it has more negative charges than positive charges, obviously it's going to be negative. And the opposite is true if the whole thing is positive, right? That would mean it needs more protons than electrons. It's a pretty simple concept. And in a chemistry class, a lot of times these kind of questions come with numbers. Like, is it a positive 2 charge or is it a negative 1 charge? And in this class, you don't need to worry about that. The few times we talk about it, you just need to know what makes something more positive and what makes something more negative. Forget the numbers, just know positive and negative. Positive means there's more protons than electrons. Negative means that there's more electrons than protons. And when you study it, think about different ways to say the same thing. So if I say I have a neutral hydrogen atom, let's just go with gold. If I have a neutral gold atom and I want to make it negative, what can I do, right? So think about the different ways of saying that. If you want to make it more negative, you could add some electrons, but you could also subtract some protons, right? So just think about that when you're studying it. And again, there's not going to be much of this on the exam. So if this stresses you out, study it, but just know there'll be like a couple questions. Like, you know, if you just can't get it, don't stress it. Just keep moving. So any questions about this slide? All right. So again, we're talking about the structure of the atom. We talked about the three basic parts. Now let's talk about the nucleus. So the nucleus is the central core of the atom, like the middle, right? Which is interesting because when you talk about cells and biology, the nucleus is also kind of like the central spot of the cell. So same here. The nucleus is the central core, and what would you find in the nucleus? You would find protons and neutrons, and you do need to know that. So there will be a test question where we say, what is found in the nucleus? It's protons and neutrons. Where can the electrons be found? Outside the nucleus. They just move around the nucleus. And here's a little something your book doesn't tell you about, but I'll tell you because we were talking about radioactivity. Here's a picture of uranium. Not that you need to know this, but there's 92 protons in there. And what charge are protons? That part you do need to know. What charge are protons? Good, positive. Now, have you guys ever tried to put two of the same poles of a magnet together? They've got the same charge, right? What do? Yeah, they repel each other, right? Positive or like things repel each other. Positive repels positive, negative repels negative. So when you think about this, you've got 92 positive things squeezed in there. 92 things that don't even want to be close to each other because they repel each other. So you can imagine it's taking some sort of energy, right? A lot of it to keep that thing together. And that's what radiation is. And that's why uranium is often used in things like nuclear power or nuclear bombs. Because all that energy that's holding those stuff together, if you could somehow start some sort of chain reaction where some of those protons and neutrons start leaving and some of the energy holding that together is released, that's radiation. And your book talks about what radiation is in general, but it doesn't explain that. And even though you don't need to know that for the exam, this concept of energy holding stuff together, that's going to be a really important concept in the next few chapters. So not necessarily with uranium, because we're not going to talk about bombs or things like that, but the concept on the molecular level of energy holding stuff together. However much energy is holding something together is how much energy is ready to be released once you break those things holding it together. So keep that in the back of your mind. But again, as far as uranium is concerned, that's just an example. Anyway, back to the important stuff as far as the exam is concerned. To remind you, the nucleus is where you'll find the protons and neutrons, and the electrons will be found outside the nucleus. So any questions about that?
Would it be cool to write one of the independent assignments on like Chernobyl or something?
Sure. Somebody was asking if it would be okay to write about Chernobyl for the independent work. And it would be, I think, because you could look at the chemistry of it. You know, talk about radiation.
So I'm a history guy.
Yeah. So you could also look into then the after effect. You know, all that radiation has caused mutations, which we'll learn about. We'll learn about mutations later in the semester, but it's an interesting place. I'd love to go. I'd love to study the organisms that are currently living there. Yeah, good idea. Any other questions? All right, let's move forward. Here's another picture of the same thing we've already talked about. Right there's the nucleus with the protons and the neutrons. This is helium. You can see the electrons. I like this picture better because it used to be back in the day you would see these lines, right, for the electrons where they're orbiting. But technically, they don't really orbit. Technically, they're just kind of all about. And that's when I like this cloud, because these electrons could be anywhere in this cloud. Not that you need to know that much detail, but it's in the picture, so I wanted to discuss it. So anyway, like I said, we've already talked about this. This is just a different picture of the same thing we already talked about. Okay, so remember when I first showed you that picture of the periodic table of elements, and it highlighted the carbon where it said C, and you have all those numbers, and I said I'd come back to it and tell you what those numbers mean. So here we are. And you might get one question on this. So yeah, this is some important stuff. An atom of an element, of any particular element, has the same unique number of protons. That's an important concept before you even move anywhere past that. Another way you could rewrite that top bullet point is The way I like to say it is an element is defined by its number of protons. So you can write that down if you want, store it away in your memory. That's an important concept. An element is defined by its number of protons. So if you add a proton to something, you've changed the element. So if you can see up there, helium, its number is 1, right? It has 1 atom. Excuse me, good grief. 1 proton. If you add a proton to that, it is no longer, did I say helium or hydrogen? Good grief. We'll stick with that. Helium has 2 protons. So if you add a proton to helium, oh yeah, it's right there. If you add a proton to helium, it is no longer helium. It would then become lithium because, again, it's defined by its number of protons. If you were to take a proton away from helium, it would then be hydrogen because, again, I'm trying to impress this upon you. The element is defined by its number of protons. If you change the number of protons, you change the element. The technical word for this is the atomic number. So the atomic number of an element or of an atom, in this case, those words can be interchanged. The atomic number tells you how many protons are in the element. And again, in this example, we're talking about helium. Not that you need to know anything about helium. It's just a great, easy example because it's a small number. But yeah, again, if you add a proton, you change the element. If you take away a proton, you change the element. So make sure you know what the atomic number is. And if that was on the information I give you, or that I was giving you, I would think that's relatively easy information. That would be easy to remember. But it gets a little bit more complicated. Because then you have something called the mass number, which is almost sounds complicated, right? Because atomic number is a number of protons. I'm going to say a mass number, and you would think, all right, mass, number of protons, that makes sense. And there is a relationship, but they're not the same thing. The mass number is adding up the protons and neutrons. So again, helium is a great example. Here we go. Again, helium's atomic number is 2, meaning it has 2 protons. Now, if it also has 2 neutrons, 2 plus 2 equals 4. So its mass number would be 4. So for now, while you're looking at this slide, you can ignore that one at the bottom right. Because right now, this one shouldn't make much sense to you. You know what the atomic number is. You know the element symbol. And then here, this is something different. Atomic mass. I haven't talked about atomic mass, right? And you can see here that the atomic mass of helium is 4.003. But the mass number of helium is 4. But again, they're very close, but they're not the same. And we'll talk about this one a little bit later. Before I move forward, there will be some test questions on this, maybe like 1 or 2 basic math questions. And there already are some on the exam. The study guide. So you might get a question where I say helium's mass number is, or helium's atomic mass is, good grief, I can't talk today. Helium's atomic number is 2. All right, that's the first bit of information I give you. And then your brain, you should say, okay, that means it has 2 protons. And then the next question the next part of the question might say, helium's atomic mass is 4. Therefore, how many neutrons does it have? And you'll get a basic math question like that. And I like it because, yeah, it requires math, but math isn't the point. The point is that you memorize and can apply this information. So if I say the atomic mass is 4, or the mass number is 4, and the atomic number is 2, then you should think, okay, has 2 protons, its mass is 4, and the mass is the protons plus the neutrons. Oh yeah, that means there must be 2 neutrons. Does that make sense to everybody? So again, you don't need to memorize this, the helium as the example. You just need to know what the mass number is, you need to know what the atomic number is, and you need to know the relationship between them, because there will be 1 or 2 questions where you have to apply that. And again, there's questions on the study guide that have that. All right. So any questions so far? Okay. So again, let me back up. Bottom right, you can see the atomic mass of helium is 4.003, which is different but close to the mass number, which is 4. So then let's talk about what atomic mass is. Like I said, it's close to the mass number, but it may be different because it represents the average of all naturally occurring forms. And what do I mean by that? Hydrogen's a great example. There's protium that has 1 proton and no neutrons. There's deuterium that has 1 proton and 1 neutron. And then there's tritium that has 1 proton and 2 neutrons. So if you were just talking about mass number, not atomic mass, which is what we're currently talking about, if we were talking about mass number, like we were talking about on the last slide, and I showed you a picture of this, and didn't give you this information, I would say, what is the mass number of this? And the answer is 1, right? Because there's 1 proton. And if I said, what is the mass number of this? You would look at, and you didn't see this, you'd say, okay, 1 proton, 1 neutron, 1 plus 1, the mass number is 2. If I give you a picture of this and say, what is the mass number? 1, 2, 3, right? That part would be easy. You'll never have to calculate the atomic mass, but you do need to know what the atomic mass is in general, so you understand what it means in nature. So again, what you need to know for the exam is the atomic mass represents the average of all naturally occurring forms. So let me go way over here. Again, we're talking about hydrogen, and if you're online, sorry you can't see this, but hopefully you'll hear me say it. We go way over here to the periodic table. I'm not wearing my glasses. They're here, but they get fogged up. Okay, the atomic mass of hydrogen is 1.008. 1.008. What that means, again, that's the average. That means in nature, I can tell that there's a lot of these and not many of these, right? Because it's 1.008. Meaning if you looked at all the averages, like looked at all the hydrogens in the world, you're going to find a lot of these because its atomic mass is 1, and even fewer of these because its atomic mass is 2 and 3. Sort of like humans. How many how many fingers, and I include thumbs, how many fingers does the average human have? You would think 10, right? But that's not true. Just think about it. Some people have extra, some people have fewer. So probably the average human, therefore, might have 9.0001, right? Not to say that we all have 9.001 fingers, right? What that's saying is if you look at all the hands in the world for humans and did the average, right? Most hands would have 10. Very few might have 9. Maybe even fewer would have 8. Same here. The fact that its its atomic mass is 1.008 simply indicates that most of them are probably this. Now, that's a lot of information, and I talked a lot about it just because I want you to understand it. But like I said, you'll never have to calculate the atomic mass. I just want you to understand what the concept means when you see it on a periodic table. And we'll talk about that finger thing here in a second. Even though we already said it, we'll talk about it again in a second with pictures. And that brings us to something called isotopes. Basically, we've already talked about isotopes. I just didn't give it a name. Isotopes are alternate mass forms of an element. That's the book definition. I think a better way of remembering it is this. If you change the number of neutrons, then you have an isotope. Right? So far I've told you if you change the number of protons, you've changed the element, right? And now I'm telling you if you change the number of neutrons, you have an isotope. They have the same number of protons and electrons, obviously, because again, if you change the number of protons, you change the element. But they behave identically in chemical reactions because, this is just for your own knowledge, I'm not going to test you on this, but the reason they behave identically is for the most part, as far as we're concerned in this class, chemical reactions happen between electrons and protons. So neutrons are kind of out of the picture for the most part, as far as we're concerned. So anyway, this is just another example. Carbon 12, carbon 13, carbon 14. You do not need to memorize anything on this chart. Just a great example of some different isotopes. Carbon 12 is an isotope. Carbon 13, carbon 14. Those are all isotopes of carbon. And again, protons plus neutrons give you the mass number, right? So carbon 12 mass number is 12. Carbon 13, 13, so on and so forth. And again, if I go to the periodic table and look at carbon, it is 12.01 is the atomic mass. That tells me almost all the carbon in the world, at least a large majority of it, would have to be carbon 12. Because if you're averaging I mean, if you average 12, 13, and 14, the answer is 13, right? But if you get trillions of carbon 12 and hundreds of carbon 13s and hundreds of carbon 14, then you're going to get something like that, 12.01. Anyway, I'm not going to ask much about atomic mass on the exam, I promise. But you do need to know what an isotope is. And again, if you change the number of neutrons, then you made an isotope. And to back it up to what we've already said, if you change the number of protons, you change the element. So any questions so far? We're almost to a stopping point. Here's what I was talking about the hands, or maybe those are feet, but again, and that's photoshopped. But still, there are some people that have extra fingers and extra toes, and they have fewer finger and fewer toes. So again, the average, when you think about it mathematically, the average human does not have 10 fingers. Now, if you use the word average in a non-mathematical sense, like, hey, if you just pick out the average human and look at their hands, how many fingers do they have? In which case, I think it was you that said 10, right? In which case you were correct. So if you mean average that way, then yeah, the average human probably has 10 fingers. But mathematically, if you would take all the hands in the world and count all the fingers and then make a mathematical number out of that, then it probably would not be 10. But anyway, any questions about isotopes or atomic mass or anything like that? Your book also talks about radioactive isotopes, but I'm skipping that. Basically, the easy answer to that is you already know what an isotope is, which is if you change the number of neutrons, you made an isotope. Radioactive isotope is just an isotope that's radioactive. It's literally in the name. So anything you read in the book, if you're taking notes, you take some notes here saying, go ahead and read this. But as far as studying it and memorizing anything for the exam, you can skip all the stuff about radioactive isotopes. Every chapter has this thing called the process of science. I highly recommend reading it so you can get your brain thinking scientifically, that it'll never be on the exam, so I will always skip it. But if you happen to read it and say, oh, that is actually interesting and I have some questions about it, then let me know and we'll talk about it. And that's it. So when we come back on Friday, hopefully we can finish by talking about chemical bonding and then water. So any questions? All right, we're done for the day. If you need me, I'll be online for office hours from 9 to 10:40. And don't forget to email me for attendance.
For the points today or this week, is that just the independent work and then the study guide thing?
Yeah, and again, study guide kind of falls under the independent work category. So if you do study guides, you get a few, get some points towards your independent work. Technically, you don't have to do the study guides. If you want to get your independent work points elsewhere, you can. But I recommend the study guides because I take those and that's what I use to write your exam. So I recommend it.
Is our first exam next week?
Tentatively, it would be the week after next. Because if everything goes to schedule, this week we'll do chapter 3. Next week we'll do, this week we'll finish up chapter 2. Next week we'll do chapter 3. And the following week would be the exam.
Okay.
Good questions.
It'll be on Monday, Wednesday, or Friday.
Someone here just asked what day it'll be on, and we'll talk about that when we get there. Usually once we get closer to the exam time, I usually send out some poll to you guys and say, what day do you want? And I might even try something different this semester. And I'll talk to you guys about this too and give you the option to vote. But I'm thinking about making the exams a little bit harder, but also not making them timed. Like, all right, this week you've got all week to do the exam, But I would have to make the questions hard enough to where you're not like I wouldn't say, what is the mass number? And you just look up the definition, like, oh, that's the mass number. I would have to make up some questions where you have to like use the mass number, if that makes any sense. I would have to come up with questions where you apply the knowledge that's in the textbook, as opposed to just being able to look it up and be like, oh yeah, the oxygen's 96% of your body weight or whatever, So anyway, we'll talk about all that in the future. Any other questions?
As far as independent work goes, it said we only need to write like a page a week, right? So what if I end up writing like 4 pages about the subject?
So the question was, if you're still online, he was asking about independent work. The general guideline, just for grading purposes, is to do about a page a week. more specifically, you need to have 10 points per week, however you get it. If you do more, that's great. If you do less, technically it doesn't hurt you. The only reason it matters is because sometimes people will ask in the middle of the semester what my grade is. So if you ask me on week 4 what your grade is, technically you should have 40 points worth of independent work. And if you don't, that'll affect your grade at that moment that you ask me. That makes sense? The only reason it's there is for when people ask me, hey, what's my grade? That's the only reason I say 10 points per week. Technically, and I really don't recommend this, technically you could wait till the last day and try to turn in 100 points and it wouldn't hurt you at all, technically. But again, when you come to me next week, which is week 3, right, and you should have 30 points worth of independent work. And if you don't, then at that moment when you ask me what your grade is, it'll be a little bit lower than it should be. But yeah, there's definitely no minimum. One person's really rocking it out on independent work. They're almost halfway done. So yeah, definitely no minimum. You can write whatever you want.
Your question is like, if I just write like 5 pages on one subject.
That's completely fine. Yeah, you
Sometimes I just get rolling. And
Yeah.
I'll end up writing 10 fucking pages about how to fix the U.S. economy.
Yeah, you can do 5 pages on one subject. There is no minimum or maximum when you're writing a paper. You could write 3 sentences. You could be like, I heard somebody in class talk about Chernobyl. I didn't know what it is, so I looked it up, and according to the website, it was this, right? That's a 3-sentence paper. It wouldn't get you hardly any points, but you could do it. So yeah, no maximums, no minimums. Just write to where it's pleasurable. If you feel like you're getting a little bit bored in writing it and want to stop your paper, go for it, however long it is.
It doesn't really matter what we write about.
As long as it's about biology. Yeah. All right, it's 8:49. I'm gonna get off. Like I said, I'll be back on for office hours from 9 to 10:40. If for some reason I'm a little late, because sometimes my computer won't log back in without giving me problems. Like if I'm 10 minutes late logging in, then I'll just stay a little bit 10 minutes longer. So I'll let you guys go. Like I said, don't forget to email me for attendance. And if you need me, I will see you sometime after 9.